Hello, my name is Lavrenti Gutsev, and I would like to quickly show you our most recent research. Previously, we performed joint work with Pavel Troshin's group where they prepared a formidinium lead chloride resistive sensor device which was selective towards ammonia. The nonlinear response of the device indicated that the likely mechanism of sensing was the saturation of sites which accept the gas analyte, so the defect. In our theoretical analysis determined that there is a trap state present just below the conduction band when there is a chloride vacancy. Adding ammonia analyte to this vacancy yielded, while other analytes did not have a very strong effect on the electronic structure of the perovskite. So when we calculated the gas absorption energy of the ammonium into the defect site, I noticed a pretty significant discrepancy that was difficult to explain because the gas absorption energy was much lower for the formidinium vacancy when simulated at the experimental condition of 1 ppm pressure. So that was the motivation of our further theoretical work, because immediately this led us to the thought that anti-site defects must also probably play a role in the sensing phenomenon. So that is actually what our present work demonstrates. We plotted these defect formation energies for quite a few scenarios depending on the chemical potentials. But we know that for the Fermi pinning behavior, the anti-sites generally played a pretty large role regardless of which chemical potentials we used or at which temperature we simulated them. So the way we can explain our original observation is that we have an anti-site defect paired with a vacancy. This is a likely explanation for anti-sites in these materials anyways, since the most mobile defect of the material by far are generally the halide vacancies. The paper we're currently writing is kind of a technical work. So we did our due diligence and we calculated the defect transition energies, which is customary in such works. But we also wanted to know how important is the dielectric screening correction, which is generally called the Markov-Payne correction. But if you don't include the multiple correction, it's called just the Madelung correction term. And the conclusion we came to is that it does matter a lot, because here we can see that when we have the lead vacancy, the high oxidation states, -2, -1, actually only intersect, so they only have a defect transition energy when we include the correction, but they actually don't show up as a defect transition energy at all if we don't include the correction. So what we can conclude is actually this dielectric screening correction is important to include at least the first term of this correction. So thank you for your attention, thank you for listening to this short report, and I will be taking your questions now.